Hello, this is section 2.1, day 2, the derivative in the tangent line problem. So we're going to continue our conversation that we had with day 1 of these notes. And you can see it starts off, first example, find an equation of the tangent line to the graph of f at the indicated point. So this one's a little bit different because I want the equation of the tangent line. Okay, so what we worked on day 1 was finding the slope of the tangent line. So in this case, I actually want the equation of that tangent line. So we'll still need the definition of derivative to find the slope. And then we'll be able to use that to find the slope. And then, of course, this ordered pair to write the line. So that's the first thing we do, is use the definition of derivative. So this is your f of x plus the change in x right here. And this is minus f of x all over the change in x, with the limit approaching the change in x approaching 0. So you could say, well, Cogswell, we're finding the derivative at -3. Could we use that limit process with the c? Yes, you could, and you could plug in -3 for c and use that to get the specific derivative at this point. The nice thing is, what if I ask for this and the very next problem I say, oh, now I want the tangent line at a different point? Well, if you have the formula for the derivative, then you don't have to go through this process again. So that's why we generally just find the derivative, the formula for the slope of the tangent line, which is the derivative. And that way we can now use this for any point we want. So simplify, plug in 0 for any remaining change in x's. This is 2x plus 2. That's the derivative of your function here. And remember, the derivative is that gives you the slope of the tangent line anywhere along this curve. Don't forget that. I'm going to constantly remind you of what the derivative means. So once we have the derivative, now I want to know what is the slope of the tangent line. So plug -3 in, and that's where I'm getting this -4. And then here, I'll scroll up. Now you can actually see. So f prime of -3 is -4. So that's the slope of the tangent line. And we use the derivative to get that. And we have an ordered pair that was given to us. Y minus y1 equals m times x minus x1. And if it doesn't specify how to leave the equation, leave it in point slope form. All right, and that's perfectly fine. So be very careful with what it asks for. Be really careful there. And remember, the derivative gives you the slope. And then if they had just said at x equals -3, you plug -3 into the function to get the ordered pair. All right, let's see what the next one says. It says, find an equation of the line that is tangent to the graph of f and parallel to the given line. Oh, sounds fun. So first and foremost, they gave us the line. And if it's parallel, let's figure out the slope. So solve for y. So I moved the y over. Y equals 3x. So 3, that's the slope. And for parallel, I want the same slope. And I went ahead and just added, just for review, perpendicular slope. Remember, you flip the fraction and negate, or the negative reciprocal. All right, so I came over here and I went ahead and found the derivative. Now, you'll have to cube out that binomial. So lots of fun there. But cube out the binomial, and then here's your f of x over the change in x. Factor any change of x's out so you can cancel, and then plug in 0, and you're left with 3x squared. That's the derivative. But in this case, we're working backwards. I know what I want the slope to be, so I'm going to set the derivative equal to 3 to figure out where we have parallel tangent lines. And you can see on the graph that you should get 2 answers. Okay, so, and of course we do, we get x equals plus or minus 1. And then it did say, find the equation of the line, and we have 2 lines here. So we have 2 slopes, or excuse me, 2 x values at f of 1 and f of -1. Now plug those in back into the original function up here. And then we already knew the slope, so we were able to write our 2 equations for these 2 parallel lines. Okay. All right, so then on this next one, find the tangent line to the graph, y equals h of x at the point -1, 4, passes through the point 3, 6, find h of -1 and h prime of -1. So h of -1, that's a y value. And then h prime of -1, that's the slope of the tangent line. Notice this little tick mark there, that means you're going to be plugging -1 into the derivative. So tangent line to the graph, we're given two ordered pairs. So I found the slope, and h of -1, they already gave that to us, is 4. That's just an ordered pair. And then h prime of -1 is going to be the slope of that line, which is what we found down here, which is 1/2. Okay. All right. Now, there is actually an alternative definition of the derivative designed to find the slope of a curve at one specific point. And we've already done one of those. We did the limit process, but this is something different. It's not quite as cumbersome as the x plus the change in x version that we have done. And I'll show you how here in a second. So in this case, the alternative definition of the derivative of f at c is this f prime of c equals the limit as x approaches c of f of x minus f of c all over x minus c, provided this limit exists. Note, if it fails to exist at a particular point, the function is said to be not to be differentiable. So if there was an asymptote or maybe a jump in the graph or the function's not defined, then it's not going to work. Okay. So the limit definition was the change in x as it approaches 0. So it picked another point on the curve and it got closer and closer and closer. It looked at the slope of the secant line as it got closer and closer. This problem is looking at the slope on either side as you get closer and closer to C. Okay. Now, where this is going to be beneficial is proving that the derivative does not exist, that the derivative fails. Right, so find the slope of each function at the given value of x using the alternative definition of the derivative. And we say here, actually, we're going to look at some situations in which the function will have a point at which it's not differentiable, and you're not able to find the slope of a particular point. Okay. So here's what we're going to do. So f of x is x plus 3 over x squared minus 9 at x equals -3. So already we know there's an issue. Right, it's not defined. So we're going to use this limit, the alternative definition of the derivative, to help us show that. So the f of x is here, and then minus f of c. So we plugged -3 into the function over x minus 3. Okay. Now you'll notice you can't plug -3 in, but so let's do some simplifying here. So in this case, this simplifies to 1 over x minus 3, but over here we have a serious problem. 0 over 0. That's not possible. Something's wrong. So if this happens to you in your limit, the limit does not exist. So it does not exist, so f of x is not differentiable at x equals -3. Now, I can understand where you might say, Cogswell, we could have said that this function isn't continuous at -3, and we could have stopped right there. And you're right. But this is showing you how, if you were to use this alternative definition of the derivative, you'll end up with, it doesn't exist. The limit failed. So here's where it's really more beneficial. So in this case, you've got a function, and you've got what's called a sharp turn. Never put that on a test, though. That's just a descriptor, right? But in this case, think of it this way. If you're standing at this point, are you increasing or are you decreasing? You're both, but how can you be increasing and decreasing at the same time? Another way to look at it is you would be able to draw or sketch all these different tangent lines through that point. But I like the argument of, are you increasing or decreasing? But let's see how it shows up with that alternative definition. So in this case, limit as x approaches -3. Here's the function minus f of c over x minus c. And you can see this ends up being 0. And in this case, if you were to graph this, you would see that you're approaching different values from the left and the right at -3. So it does not exist. Limit does not exist. Therefore, it's not differentiable at -3. Okay. So graph this so you can get the visual of how it approaches two different values from the left and the right. All right, now here's another interesting one. So f of x equals x to the 1/3 at 0, 0. So you might say, there's no issue with this. What's the issue? So if you do the limit as x approaches 0, f of x minus f of 0 over x minus 0, you get this function. And technically, if you reduce this, you get 1 over 0. Oh, that's not good. So the limit, or definition, so f of x is not differentiable at x equals 0. Now you might say, Cogswell, 1 over, this was that whole problem we did in that one section with smaller and smaller numbers, and I agree with you, but 1 divided by numbers that are getting smaller and smaller, remember what it ended up being? It ended up being infinity. That means the limit doesn't exist. So what on earth is going on? What's wrong with this problem? Well, guys, notice the tangent line is vertical. That's not good. The slope is undefined. That's why it's not differentiable. So when you have a vertical tangent line, the slope's undefined, therefore not differentiable. Okay. All right, so differentiability implies continuity. So if f is differentiable at x equals c, then we know f is continuous at x equals c. But be careful, the converse is not true. The converse of this theorem is not true. Continuity does not guarantee differentiability, and we just saw that with these two examples. It wasn't differentiable at this sharp turn because you can't be both increasing and decreasing at the same time. And here we have a vertical tangent line right there. So these had points where they were not differentiable, but they are continuous. So you have to be careful. So differentiability rules, a function is not differentiable at a point of discontinuity. So asymptote, hole in the graph, a jump in the graph, a point at which its graph has a sharp turn. But remember, don't put sharp turn on your tests, all right? So you'll want to say the slope from the left does not equal the slope from the right. This is the proper, this is slang. Think of this as slang. This is what you want to say. The slope from the left, which is what's here, the slope from the left is negative and the slope from the right is positive. So the slopes are different from the left and the right. This is the proper notation. Okay. Or a point where the graph has a vertical tangent. And that's what we saw here. The slope of that tangent line would be undefined. Okay. So this alternative definition of the derivative is going to be very useful in showing that it's not differentiable. But it is a way to find the slope of a tangent line at a specific point. But that's not very helpful in the grand scheme of things. It's a lot more helpful to be able to find the formula for the derivative. And then we can use it for all of the points that it's defined. Okay, so very useful in showing it's not differentiable. Okay, so please email me if you have any questions and make sure you're doing your homework.